Oh, hi.
Hello.
You can turn on your. Okay. We're in the study room.
Oh. Okay. Sorry, I was having trouble connecting to the internet. I had to reset my router, but I am here now. Okay. How is everybody doing?
Lagging.
I'm gonna turn mine down and I'll just listen to you.
Okay. So I was wondering if you would be able to help. I'm not like give us the answers, but like I just need a little bit of like guidance on the take home exam. So maybe I could show you some of my answers and you could just like let me know if I'm in the right direction and everything.
Because this is being recorded.
Oh, well, can we do it after you stop recording then? Maybe?
Yes. Well, individually.
Okay.
But I can, if you have questions, I can give direction. Let me, 1 second, let me get the book. 1 second. Which questions are you struggling with?
So, I don't want to say all of them, but
Well, that's good. I mean, do you want to say all of them and you're just not saying all of them?
Yeah, I want to say all of them. I have an answer for most of them. Number 3, I got X, but I don't know if it's right, so I just wanted to know if I'm going in the right direction. And for number 2, I did A and C, but B is kind of confusing. And I just wanted to like check to see if like the answers are even close to being right or anything, you know?
Okay. So like I said, those more specific questions about like your problems, we can go over individually just because, yeah. Want to give everybody their chance to try the problems out on their own. So you're having trouble with number 2B?
Yeah. So
Okay.
I got a Half-Life. Do you want me to tell you what I got for the Half-Life or?
Well, A, you would have gotten a Half-Life.
Yeah, I got
It's okay, you don't have to tell me what it is.
Okay.
But you will use that in B. So once you have your Half-Life, so it's talking about, so we've got a biolate, blah, blah, blah. It's telling you 250 milligrams. So it's asking how many years will have gone by in order to get from the initial mass, 4.755 grams, down to this biologically acceptable mass, to about 250 milligrams. So if we look on the, 1 second, on the test handout, we should have all the equations we need for this problem. Okay, and they're the only 2 equations on here. Yep. So, oh, the test handout itself. No, I'll share my screen.
I didn't get that.
That's the one. I think it's that one. That's where it's at.
This one right here. Yes.
I didn't get those.
Well, I thought I handed out at the review, but this is also on D2L.
Oh wait.
So I think it was the one you just showed me a second ago.
Yeah, I don't have the periodic table though.
Oh, the periodic table I didn't print out.
Okay, cool.
This is just my copy, my electronic copy. And if you look on D2L, the periodic table will be there as well. I just print out one, and then I have this periodic table printed and laminated for the tests, so I could get them all in color and be pretty. But so I'll be providing this periodic table. So this is the exact periodic table that I'll be providing. But we see, so I'm assuming you used this equation right here. Let's see if I can Where is the little?
I did not use that formula at the bottom to determine the half-life. I did the natural log thing to get the K constant. The one in the textbook?
Oh. So okay. But your K is your rate constant.
Yeah, and then I use that to do like the K equals 0.693 over T, and then I solved for T.
Okay, that
Would that still give you?
that would, this is simplified right here. So well, I guess you use both of these equations. It'll, I would assume, give you the same value. I would, yeah. So
What's N?
so N is number of half-lives. So, and I'll just do an example with it. So, let me share a different screen. And then,
I guess.
I mean, I'm pretty sure you could use the same exact equation that you used in the book, or the equation used in the book should be fine.
Yeah.
I usually just provide these because they're a little bit easier to use, and then you don't have to use the K value, which we haven't really talked about. Okay, so let's say we have, so the equations that we have here are A equals A naught 1/2 over N, or 1/2 to the N. And then T is equal to N times by T 1/2. So the A is amount. The A naught is initial amount. And then T is time. T 1/2 is half-life. A and A naught are the same unit. T and T 1/2 are the same unit. And then there's N, which is number of half-lives. Sorry, I know this is somewhere in my notes, but you guys aren't required to read the notes. I guess I should have pointed this out. So let's say we have an initial amount of 150.0 grams and an amount of 0.175 grams, 1750 grams at time t. Right? So we would put these two numbers into this equation first. So our A 0.1750 grams will be equal to our A naught 150.0 grams times by 1/2 to the N.
So amount is like the current amount, and then AO is the original amount.
Yep, however much you start out with.
Okay.
And when we put this into a calculator, there's one. We get, so we take 0.1750 divided by 150. That gives us 0.001611667 equals 1/2 to the N. And then how do we bring down an N, an exponent?
It's the natural log, right?
Yeah, natural log. So we'll take the natural log of both sides, which probably ends up why those equations are pretty similar. It is a first order process, so it should be fine. So we take the natural log of both sides, we get negative 6.7536 is equal to n ln 1/2. We'll then divide by ln 1/2. And we'll get an n equal to 9.743.
I'm sorry. Could you go over that last step again?
Yeah, sure.
The
So,
-6 to the end.
so at this point, we're going to divide both sides by ln, and I'm just going to do 0.5 because it's the same thing as ln 1/2. That'll cancel that out, right?
Mhm.
And then when you take ln, or when you take negative 6.7536, divide it by the natural log of 0.5, which would also be a negative value, you get n equal to 9.743.
So n is,
In,
what is n? Like t is time, a is
oh,
amount.
sorry,
What is n?
I didn't mean to put years. This is times. So amount of half-lives.
Okay.
that have occurred, I guess.
Thank you so much.
No, not a problem. I should have directed you guys to these equations because these are just a little bit easier than the ones that are in the books. Either one should give you the correct answer, though. Hopefully. I'll look at yours afterwards. If and anybody else who might, I can look at yours as well.
What is
actually, if you want to just send me a picture and email it to me,
okay?
I can look at it and tell you during this.
Okay. Is there a way to determine how much of a given substance is considered safe?
It would have to be a told value. Well, and the problem is saying that 250 milligrams is a biologically safe amount. So that would be your A.
Oh.
And now we're not, with the first part of the problem, we're not done. So after you get this N value, you then need to figure out how long the half-life is. So you're going to use your second question, your second problem, which is T is equal to N times by T 1/2. So let's say the time that has gone by is 425 years. Right, so let's say that 425 years has elapsed. We'd put that 425 in. That'll be equal to our N, 9.743, times by our T 1/2, which is what we're solving for. And that T 1/2 is going to be the same unit as the T, which is in years. So we'll essentially take that 425, divide it by our N, and we get a T 1/2 equal to 43.6 years. So that means after 43.6 years have elapsed, one half-life has occurred.
So,
Yes. Sorry, I'm just checking something real quick. But you can talk. Go for it.
Could you use the T equals N times the half-life to figure out B? Is that how you figure that out? Or
so with B, let me bring it back up. So with B, this is going to be your A value. This is still your A naught.
the 43.6?
43 point, huh?
What is the, I'm sorry.
Wait, is it showing the right screen?
Yeah, it might be frozen.
I might have, oh. Sorry. No, I just forgot to do a new share. Let's try that again. Okay, so the 250 milligrams, that is your A value for B. Your 4.755 grams, that's your initial value, your A naught. You got your half-life from A, right? So you got whatever your half-life was here. And at this point, you're trying to figure out how many more years it would need to decay.
So the 254.2 is the AO.
Oh, yeah, sorry.
5, 4.
That was the initial AO and
And then
A.
it's
But yeah, this is A.
to the end. So then the N value would be the answer to B.
The N value would then be used in the T equals N times by 1/2 to figure out your T.
Find the number of half-lives, and we have to put that in with our half-life, and then we'll get how much more time.
Yeah, you're going to be solving for N again.
So you solve for N and then you solve for T and then T is your answer.
Yes.
Hold on.
Word.
Yeah, you're essentially using the same two equations every problem, A, B, and C. And it says more years, so you can use that 4.755 grams as your A naught. Because you already figured out how many years, you already know how many years went by between this and this. That was for part A. And then for part B, you already have this amount and you're going to this amount. So it says how many more years beyond that time. Does that make sense?
And did you say we need to use those equations for C as well?
Oh no.
Okay. You scared me.
Sorry, I just didn't read first before I said stuff. Yeah, no, this will just be writing out the actual decay equations.
And sorry if I'm like holding up the review and stuff, but for number 3, so I did the whole like so how do I even explain what I did? So I did the atomic AMU, that's atomic mass unit. I did the AMU of 95x plus the AMU of 102x plus the AMU of 98y, and then I had that all equal 98 point the 108 thing because that's your total mass, and then I isolated y and then put x in terms of y.
Yep.
And then I solved for.
You're going about that the correct way.
And the thing is,
just send me a picture of your work if you don't have a specific question.
Okay.
Again, just because this is a test, so.
All right.
But you can send me a picture and I can see if you're going in the correct direction.
Okay, thank you.
Not a problem. I mean, I don't want to stop you from asking questions, just I don't want you to go through all of your work.
Yeah. I think that's all that I had. Do you guys have questions? Or?
For number 3, you have 2 unknowns, and you use x and y, and then you'll have to, use the idea that x plus y is equal to 1. Or 100.
So I did 2x plus y equals 1 because they both have the same. Okay.
Sorry, yes.
Well, once I divided it by 2, because it's 2x, so you have to do 1 minus y over 2. Once I divided it by 2, I got a much bigger number than what I got initially when I didn't divide it by 2. So I don't know if like the big number or the little number is right,
Just send me your work. I'll look at it.
Okay. Huh? No. Do you guys have any questions about the exam or anything? I don't mean to be like the only one asking questions.
For this part, I think we would be
Like a take home. Yeah.
Do you have questions about the actual exam?
You said that the actual exam was going to be mostly conceptual, like the scientists naming the compounds.
So I'm going to go through kind of the content in so this review, the whole purpose of it is to kind of go through. It's almost like a study guide review where I stop at points where you guys want me to explain.
Okay.
So at any point that you guys need me to go further in detail, that's when you're like, hey, I have a question about this. But I'll basically be going through and kind of pointing out things that you guys should know for the test. Now, I use, when I talk about this, I use the actual Brown and LeMay book. So the ordering might be a little bit different from the OpenStax. But I will be making sure that I go through the OpenStax and making sure that all of the questions I ask are also addressed in the OpenStax book. Okay, so let me go ahead and share this screen again.
This was like $200 used.
Yeah, it's an insanely expensive book, which is why I do the OpenStax as well.
I want the iPad Pro so bad because you can download PDFs of textbooks. If you find the right websites, you can get them all for free and stuff. So
that's what I use for my reviews. I love my iPad Pro. It's my favorite thing. I use it all the time. Okay, sorry. You can also draw with it. Not that I'm good at that, but it's fun. Okay, sorry. I digress. Here we go. So in this test, we are going to be talking about what would be chapters 1, 2, and 21, which covers modules 1, 2, 3, and 17. 17 seems weird, but not everybody goes over nuclear chemistry, and I had to make this as a template for people last summer, so that's why it's 17. So in chapter 1 or module 1 and 2, we talk about matter, energy, and measurements. That's kind of the whole purpose of that. So with this, you should kind of know, of course, the definitions of matter. You should know what matter is, everything that has that occupies space and has mass. You should also know the different properties. So with properties, we have intrinsic and extrinsic. So you should know the definitions of those. And then there's also physical versus chemical. So again, you should be able to define properties based on whether they're intrinsic or extrinsic, physical or chemical. There's no set one that it could be, like it's not always intrinsic and physical or extrinsic and chemical. They're going to be mixed around. So you should be able to anything, like if we talk about mass, you should be able to talk about that as intrinsic, extrinsic, or physical or proper, or intrinsic or extrinsic, physical or chemical. So mass would be a extrinsic physical property, right? Or if we talk about flammability, what would flammability be?
Chemical extrinsic.
So is it dependent upon the amount?
Chemical intrinsic.
Chemical intrinsic. So flammability, so with intrinsic versus extrinsic, intrinsic is going to be something that's independent of mass, right? And it's going to be determined by the material itself. It's a kind of chemical identifier. Physical versus chemical. Physical is something we can observe without doing a chemical reaction. Chemical is only observable during a chemical reaction. So we can only know how flammable something is by setting it on fire. You should know the difference between elements, atoms, molecules, and compounds. Right, so if we're talking about element, we're talking about all the atoms of a specific atomic number. If we're talking about an atom, that is just an individual atom, and it is, we usually talk about this in terms of monoatomic, right? So if we're talking about atoms, they're one atom. Molecules, these are diatomic or polyatomic. Molecules can be either all the same thing, or they can be more than one thing. All the same atom, or different types of atoms. The thing that's going to determine if it's a molecule is it has to have at least 2 atoms or more, and they have to be non-metals. So this is going to be covalent, covalently bonded. With our compounds, these are diatomic or polyatomic. And these have to be different types of atoms. So you have to have at least 2 different types of atoms with the compound. But compounds themselves can be covalent or ionic. Right? And all of these atoms, molecules, compounds, and elements are all considered pure substances. If we take 2 or more of these pure substances and we combine them, we get a mixture. Well, if we combine them and a chemical reaction does not occur, we get a mixture. And then with our mixtures, they can be homogeneous or heterogeneous based on what we can see.
Oh, yeah, all of them.
Is there a question?
Mm-mm.
Okay. We also looked at the states of matter.
Can I? Sorry.
That's good.
But homogeneous is when they are like joined together but don't react with each other, and heterogeneous is when they are like they retain their independence and they also don't react with each other, right?
Kind of. So
Yeah.
I
Like you can't see the difference with homogeneous.
yes.
Okay.
Homogeneous, it looks like one substance.
Okay.
In both of them, we don't have a chemical reaction occurring. They both retain their own properties, right? Both substances can be separated through physical means, filtration or evaporation, something like that, or some sort of chromatography technique. So they can be separated without performing any chemical reactions on them. That's just a mixture in general. Heterogeneous, we'll be able to see the different components. So something like blood would be considered heterogeneous because it will eventually, if you leave it long enough, it will, the blood cells themselves will fall out, and you'll see the different components. And it's not something that happens very easily. We call that a suspension. Right, so if you can see the different components, granite is a great example of a heterogeneous mixture, right? And then a homogeneous mixture, it doesn't matter if it's clear or cloudy, as long as you can't see the different components. Air is a homogeneous mixture. Water is a homogeneous mixture, unless we're talking about pure water. But any tap water you drink is definitely a homogeneous mixture, unless you live in like Detroit, then it might be a heterogeneous mixture. Okay, does that make sense? Our states of matter, we have gas, liquid, solid. With the gas, high energy, they're moving very, very quickly. They have no fixed volume or shape. They are they're compressible, so they can be compressed, they can expand, and they are going to be the least dense out of all the states of matter. Liquid, that is going to have a set volume, but not a set shape. It's going to take the shape of its container. But you can't take a liquid from a smaller glass, pour it into a larger glass, and get more liquid, right? So it's got a set volume. It is still a fluid. So gas and liquid, both of those are considered fluid states because they're moving throughout, right? So there's constant mixing that's going on in liquids and gases. Liquids are high energy, not quite as high energy. Liquid particles are high energy, not quite as high energy as gases, but they are constantly moving and tumbling over. The particles are constantly moving and tumbling over each other. With a liquid, the density is much greater than in a gas, right? So with a gas, the particles, we consider them to be infinitely far away from each other, but with a liquid, they're right next to each other. And then a solid, that's gonna have a definite shape, definite volume. There's little movement that goes on in a solid. Really with a solid, all you get is vibrations. You don't actually get them tumbling. So we no longer consider a solid to be a fluid. It's much lower energy. All we have is vibrational energy. And I'm pretty sure I just said definite shape and definite volume, but just in case, neither a liquid nor a solid can really be compressed. They also don't really expand. Maybe small amounts with extreme temperature changes, but nothing significant. Okay. We already went over elements, compounds. You should be familiar with law of constant composition and law of definite proportions. Really all of the laws that we go over in these. Let's see. Beyond the definitions of those, not a really big issue with those. Oh, sorry, 1 second. Hello. You should know what a solution is. A solution is a specific type of homogeneous mixture. It's the one that we talk about the most. With the solution, like I said, it is uniform throughout. And it is also clear, not necessarily colorless, but it will be clear. We talked about physical and chemical properties, intensive and extensive properties. We also looked at different types of changes, specifically physical and chemical changes. So with physical and chemical changes, our physical changes are essentially the changes that occur to it visually, right? Without changing the actual substance. So something like evaporation. Is that a physical or a chemical change? Oh.
Physical.
Physical, why is it a physical change?
Because it's still H2O.
Exactly, we haven't changed the actual molecule. So with a physical change, we can change its appearance, but as long as it's the same molecule or the same compound, we have not undergone a chemical change. So a chemical change, we usually see that by a color change. So technically a color change is not a chemical change, but if your substance has a color change, almost always that's going to be indicative of a chemical change. So like painting something would be a physical change, but dissolving, so if you look in the book on page 13, they take a penny and they dissolve it in nitric acid, but it's not really dissolving, right? It is chemically reacting. You're forming copper, what is it, copper 2 nitrate. So that's a new compound, but you can see a color change. It goes from clear to blue. So that's a pretty good indicator of a chemical change. And heat, a lot of times the production of heat is also indicative of a chemical change. Looking at separation of mixtures, the types of separation we talked about are distillation, filtration, and chromatography. You don't really need to know a lot about those. Just really that those are 3 types of ways of separating mixtures. None of them are going to result in a chemical change. These are all physical changes. Where distillation, we are heating up a liquid-liquid mixture to separate out the liquid. Filtration, we have a solid that's suspended in a liquid and we can filter out the solid. And then chromatography is using some sort of stationary phase to cause components of a mixture to separate out based on intermolecular forces. So beyond knowing that these are separation techniques, and maybe just kind of having an idea of what they're separating, nothing more you really need to know about those. We looked at energy. So you should know the definition of energy. You should know the definition of work, and you should know the definition of heat. Beyond definitions, nothing more is really needed to know about those. You should know kinetic energy versus potential energy. And you should be able to look at a type of energy and determine if it is kinetic versus potential. So if we've got a ball at the top of a hill, what is it? Once the ball is hit, what is it? You know, and the idea that energy is conserved, law of conservation of energy. So energy is conserved, mass is conserved, right? Law of conservation of mass. So it's conserved. So if we have all potential energy initially, once we kick the ball off, that potential energy gets transformed into kinetic energy. And then once we're down at the bottom, we've gone all back to potential energy again. You should know all of your metric prefixes from femto all the way up to peta. You should know the prefix name or the actual prefix, its abbreviation, and its value. So if I have a chart, for instance, that looks very much like the table on 18, or I think, and there's a handout on, so if you go under chemistry resources, there is a metric prefixes and conversion factors in there. One second, I'm trying to open it. There we go. It's got the table that I'm talking about for the prefixes. So you should be able to fill out a table that is empty, going from femto up to peta. You should know the temperature units. And if I give you the conversions, you should be able to know which you're converting into, right? So if I say equals degrees, oops, why does it keep going? degrees Celsius plus 273.15. You should be able to tell me what I'm solving for. But
Is that Kelvin?
it is, yes. So, or equals 5/9 degrees Fahrenheit minus 32. That would be degrees Celsius. So you should be able to know what's on this side if I give you the equations. You will not be doing any temperature conversion. So you should know your SI units. And you should know whether they are a regular SI unit or a derived unit. Okay, so you should know what am I trying to say? Words are hard. You should know the unit for volume, the unit for mass, so liters, kilograms. Kilograms is the only really weird one. Time, seconds, temperature, Kelvin. I thought there was a table in here. Maybe oh, there it is. Your temperature, Kelvin, time, seconds. That's probably about it. So if you know your length in meters, your mass in kilograms, your temperature in Kelvin, and your time in seconds, those are your SI units. Your regular SI units, and then your derived units include density and volume. So your volume is going to be meters cubed, right? Which is the same as liters. And then your density is technically kilograms per liter for the derived SI unit, though we usually use grams per centimeter cubed. You should know what precision and accuracy are. So you should know the difference between them. If I were to give you a scenario, you should be able to tell me if something is precise, accurate, or both. So you should also know that kind of our significant figures really tells us how precise something is. Not necessarily how accurate it is, but how precise it is. So more significant figures, more precise. To be something that's accurate, you have to be close to the true value, right? We can have a scale that is incorrectly calibrated and it can have really high precision with no accuracy whatsoever, right? So you should know the difference between that accuracy and that precision. You should also be able to determine significant figures, how many significant figures are in a given value. So with this, we should know that all non-zero digits are significant, and then zeros are significant in some cases and insignificant in others. Specifically, if we have a leading zero, so these are called leading zeros. A leading zero is going to be a zero that is just it's just considered a placeholder. So it is there to tell you what that number is, but it doesn't actually give us, it's not an important digit. It's just there to be a placeholder, right? It's not like, oh, this was 0 or 1. No, that is definitely a 0. It's just a leading zero to tell us what number it is. And if we were to put this into scientific notation, we would see that those zeros go away. So any zeros, essentially any zeros that are going to go away in scientific notation are going to be insignificant. If we have trailing zeros, sorry, I have to remember. These are significant only if the number has a decimal place. So if we look at 100 versus 100.0, this has 1 sig fig because these are insignificant. This has 4 sig figs because since we have this decimal here, these are now significant. So our trailing zeros are significant if the number has a decimal, and then captive zeros, these are always significant. And these are going to be zeros between non-zero digits. Okay. You should also know the rules for determining significant figures in calculated values, right? So you should know your multiplication division. Rule, and then your subtraction addition. So if we have multiplication and division, it's number of significant figures. If we have subtraction and addition, it's number of decimal places, or the last digit of precision for the least precise value. So there may be some calculations where I want you to do these rules, but they're not going to be hard calculations, right? So there will not be any significant math. There will not be any significant math on this test. The significant math is in the take home. So probably the most math that you'll see is me giving you, simple addition, subtraction, multiplication, division problems where I want you to give the answer to the correct number of significant digits. Okay, so that is a possibility, but there will not be any dimensional analysis on this test. That being said, you should know what dimensional analysis is, and you should know what a conversion factor is. Right, so you should know the definitions that are related. So you should know what a given unit is, what a desired unit is, and you should be able to explain the process of dimensional analysis and what the purpose of dimensional analysis is. But you will not need to do any dimensional analysis on this test. Okay, any questions so far? So that was modules 1 and 2. Okay, module 3, this is going to be all of chapter 2. In here, it actually talks about the law of conservation of mass, law of multiple proportions, law of constant composition, all when we talk about Dalton's atomic theory. So you should be able to kind of summarize Dalton's atomic theory or answer questions about Dalton's atomic theory. I'm not going to require you to come up with all the postulates, but you should know what they are. So there will not be a question where you're like, give me all the postulates of Dalton's atomic theory. But you might need to identify which ones are postulates or which ones are not. And you may need to if given a definition for law of conservation of mass, law of constant composition, law of conservation of energy, law of multiple proportions, any of those, you should be able to match the definition with the law. You should know all the discoveries for your subatomic particles in the textbook, because it doesn't really talk about the discovery of the neutron or what experiments led to the discovery of the neutron, but protons and electrons are the discoveries that led up to those are both within there. So it includes the cathode ray experiment, by J.J. Thomson. J.J. Thomson. So you should be able to explain the cathode ray experiment, right? We have a cathode ray. It is, we now know it is was producing electrons. So a cathode produced electrons. Those that cathode electrons, or the electrons coming from the cathodes, then goes towards the anode. And around the cathode and anode, so in between the cathode and anode, what's holding it all together is a fluorescent screen. So it's a big tube, right? Big tube. You have your cathode and your anode and a fluorescent screen. Right? And electrons are coming off from the cathode, going to the anode. And what J.J. Thomson did is he introduced a magnet. And he knew which side was the positive pole and which side was the negative pole. When he introduced the positive pole, the electron beam coming from the cathode hit the fluorescent screen. And when it hit the fluorescent screen, it fluoresced. Right? So there was a light that came about from that electron hitting. And then if he put the negative end, it would go away from that. And by varying the strength of that magnet, he was able to determine that negative particles were coming out of the cathode, which were later determined to be electrons. And by varying the strength of that magnet, he was able to determine the charge to mass ratio of an electron. Right. Next experiment was the oil drop experiment. And these were going on kind of at the same time. Concurrently, I guess you can go with. They're within like a year of each other. So with this one, you have an atomizer producing these oil droplets, and then one oil droplet at a time goes through this hole, and then they put electric plates. They turned on electric plates, and this is Robert Millikan. Is that 2 L's? I don't even know. It is 2 L's. Robert Millikan varied the charge of those two plates and balanced those oil droplets. X-rays were also introduced. So X-rays were introduced that caused electrons to be on the surface of these particles, negative charge on the surface of these particles, and he was able to balance, and he kept coming up with, whenever he varied the size of the drops, he still kept coming up with the same multiplier, which caused him to be able to determine the electron's mass. And it was very, very close. And he also, so he determined electron mass using that multiplier and the charge to mass ratio that was determined from J.J. Thomson's experiment, cathode ray experiment. Okay, so got that. At some point after this experiment, J.J. Thomson, J.J. Thomson developed the plum pudding model. So he basically said, oh, we've got a plum pudding where we have just this positive charge. And within here, we've got some negative electrons. Right. So that was his idea of the atom, the plum pudding model. So the plums, the little raisin-like things, were the electrons, and the pudding was the positive charge. So he determined it was a dispersed positive charge with the little electrons throughout. So after that, in order to kind of, the purpose was to kind of check the model to really prove the model. We have Rutherford. with his gold foil experiment. And here we had an alpha ray or alpha particle producer, which an alpha particle is a helium nucleus with a 2+ charge. So there's no electrons, there's just 2 protons, 2 neutrons. So helium nucleus, an alpha particle, was shot at a gold foil. And most of those particles went straight through and hit this photographic film. And when it hit the photographic film, you'd see a little, it would essentially act like those old photographs where it'd give a light spot. And there was very, very little deflection, like 1 degree of deflection from where the initial beam was, except for about 1 in 20,000 would deflect more than 90 degrees. And from here, this disproved the plum pudding model. Sorry, my handwriting is atrocious. This disproved the plum pudding model, and instead, what Rutherford determined, Rutherford and his graduate student at the time, they determined that most of the atom is empty space, except for a very dense positive center. So most of it is empty space, bitty, bitty, bitty positive center. It's like the size of a dime, if you put a dime on a football field. So that's the size of the nucleus versus the size of the atom. So most of the mass is in this little center, right? Like 99.99% of the mass is in the center. Well, most of the atom, like 99.999% of the atom, is everything else besides this center. So the space of the volume is like 99.999% empty, giving that 0.001% volume. That's the nucleus. But 99.99% of the mass is the nucleus. That is taking up 0.001% of the space. So if you think about density, mass versus volume, pretty significantly dense center. If it had been the plum pudding model, if plum pudding model was correct, because this positive is dispersed throughout the entire atom, there'd be little deflection at all. There would be none that would be deflected more than 90 degrees. Okay. You should also know who Marie Curie is. And you should know who Henry Becquerel is. Right. So Becquerel is the first person who really observed radioactivity. So he determined, he actually was the person who did the very first X-ray. But he was the one who found uranium spontaneously emitting radiation. And then Madame Curie, Marie Curie, and her husband actually determined what was causing the radiation was the actual uranium atoms decomposing. And then, Ernest Rutherford, the same guy who did the gold foil experiment, was also involved in all of this. But you should know essentially what an alpha particle is, a beta particle is, and a gamma ray. So you should know that alpha particle is a helium nucleus with a 2+ charge. A beta particle is a high energy electron, right? And then a gamma ray is a massless wave of energy, very, very high energy. You should know how they differ in terms of penetration depth and ionization ability or ionizability. So alpha particle is the most ionizing because it has that 2+ charge, so it ionizes things very, very easily. But because it is so heavy, relatively heavy, it has the least amount of penetration depth. So your skin will stop an alpha particle. So if you were bombarded with a bunch of alpha particles, as long as your mouth is not open, it would be completely unharmful to you. A beta particle is a high energy ejected electron. It is less ionizing than an alpha particle because it has less mass and it has a smaller charge. But it also, because it's higher energy, because it's smaller, it penetrates a little bit further. You would have to have a piece of aluminum foil, so it will penetrate the skin. And then a gamma ray is the least ionizing, but it has the highest penetration depth because it's the highest energy and it has no mass and no charge. So a gamma ray will actually go through your skin and manipulate your DNA, cause ionization in your DNA, which is why it's so bad for you. Gamma ray can be stopped by a thick piece of lead or a very thick piece of concrete, but it'll go right through you. So that's why you wear the lead vests, right? X-rays are the same idea. And again, if there's any questions about any of this, please stop me. You should know what the atomic number is, the mass number, and what an isotope is. So you should be able to define those. You should also be able to write a chemical symbol for different isotopes. You should be able to, again, this is going to be the possible simple math you might see on here. You should be able to calculate number of protons, number of electrons, number of neutrons. You should be able to also calculate your mass number, and you should be able to determine your atomic number. So kind of like that chart from the review. So you should be able to fill out a chart like that. Okay. You should know what the atomic mass unit is. We're not really going to do any calculations with the atomic mass unit on the test because you've already done it on the take-home portion. We will not be doing any atomic weight calculations, but you should know what atomic weight is. The periodic table. With the periodic table, you should be able to identify metals, nonmetals, and metalloids. You should be able to identify periods and groups. Let's see. I think that's going to be, for the most part, what we want to know. I don't think we really get into the, we don't actually get into the groups yet. Well, so some groups you should know. You should know your alkali metals, your alkaline earth metals, transition metals, halogens, and noble gases. So you should be able to identify a element in each of these. So if given an element, you should be able to tell me if it's an alkali metal, alkaline earth metal, transition metal, halogen, or noble gas. You should also be able to tell me if it's a metal, metal order, non-metal. You should know what a molecular formula is. And you should be able to determine an empirical formula from a molecular formula. So your molecular formula, that's your formula of your actual molecule. That we're talking specifically about covalent species. So something like H2O, C6H6, B2H6, something like that. That would be a molecular formula. And then your empirical formula is your smallest whole number ratio. And generally with empirical formulas, ionic compounds are always given as empirical formulas. So an empirical formula for water would still be H2O. CH would be the empirical formula for benzene, and then BH3 for diboron hexahydride. And then something like CaOH2. So ionic compounds are going to be given as empirical formulas. You should be able to predict ion charge using the periodic table. All right, so any of our main groups you should be able to predict the charge for. You should be able to name compounds. So you should know your inorganic naming. All right. You should be able to name acids. You should be able to name binary molecular compounds. So with inorganic, this would be your acids, your binary molecular compounds, and then just regular ionic compounds. So under inorganic, ionic, acids, and binary molecular compounds. And then organic, you should be able to identify an organic compound. So an organic compound is going to have the formula CXHY. I'm not really going to do a lot with that. But I do want you to be able to recognize an organic compound. And that is all of Module 3. Any questions about Module 3? Okay. With Module 17 or Chapter 21, most of this is stuff on the take home. Besides, you need to be able to balance nuclear equations. So beyond what we were just talking about with Module 3, you should be able to balance nuclear equations. So you should know, with the alpha particle, and it looks like that in a nuclear equation. Beta particle looks like that in a nuclear equation. Gamma ray looks like that in a nuclear equation. But we'll also be looking at positron emission. So a positron is just like a positively charged electron. So it'll be a 0 plus 1 beta plus, or this can also be seen as that, and then this could be seen as that. Or actually, let's get rid of the electron and the negative. There we go. So you should be able to, you should know what all of these are, right? So if I say positron, you should know the symbol for positron. If I say gamma ray, you should know the symbol for gamma ray, beta particle, that, and then alpha particle, that. And you should be able to use them to balance out nuclear equations. Oh, we also have a neutron, which may also be in there. Everything else would be given as their chemical form or their chemical symbol. So that was in there too. So keep in mind when you're balancing nuclear equations, the top and the bottom balance out. So if we have, let's try this. So if I gave you something like this, like that, we could see that the top is the same for both sides. So we know that it's a 0. The bottom, this number is greater than this number. So we need to have a -1 here. And when we see this, we know that this is a beta particle. So we can put an E here or a B. Okay. That is really, oh, sorry. You should also know definition for fission and fusion. If you see a fission or fusion equation, you should be able to identify them. So with fission, we have a large nucleus plus a neutron, and then decay. With fusion, we have 2 small nuclei. They're going to combine to give larger nuclei. So large to small, large to smaller is fission. Fusion, think about fusing things together. You should also know what critical mass is. You should know what a chain reaction is. And you should know which process fuels nuclear power plants, which process fuels the sun. So one of them is the sun, one of them is words, they're hard. Nuclear power plants. So nuclear power plants, that's going to be fission. The sun is fusion. You should also know that they use, what is the word I'm looking for? It's control rods. Control rods. Control rods to control nuclear reactions. Control rods are inserted and they are going to be neutron sinks. So with a chain reaction, a neutron hits a fissile material that produces more neutrons, which then can hit other fissile material. And as long as that is sustained, that's a chemical or a chain reaction. So a sustainable nuclear reaction where once you start it, it goes on its own. That's considered a chain reaction. If it goes to the point where it will explode, that is when we have a supercritical amount of fissile material. So beyond the critical amount, that is a bomb, right? So if we have supercritical amount of fissile material, we have a bomb. And then if we have subcritical, we do not have a sustaining reaction. So for, that's why nuclear power plants are so dangerous, because you don't want to be subcritical, because then it won't sustain itself. You don't want to be supercritical, because then it will explode. You have to be critical, right? But they have the control rods themselves are there to control a runaway reaction. So if a reaction is producing too many neutrons, and it is beyond what can be controlled by the reaction itself, they use those control rods that go into the material and they'll absorb those neutrons. With bombs, you have two subcritical amounts of fissile material, and you usually have something in between them, and you remove that something in between them, put those two together, and now you have a supercritical amount of that, and boom, you have a bomb. Okay, that's really all I want you guys to know from module 17 or chapter 21. Does anybody have any questions?
Is the test going to be like written questions or like multiple choice or both?
There is going to be multiple choice, fill in the blank, matching, and long answer. And you guys, it's meant to be an hour-long exam. We're doing it during lab, so I probably will not be rushing you guys out. So I don't envision you guys will be on a time crunch. So it's more just kind of proving your understanding of the material, not like how quickly can you show me everything you understand. It's not like the regular semester where I have a set time to give an exam. I have 3 hours to give you an exam. It will not be a 3-hour-long exam. It is meant to be done in 50 minutes. So.
Roughly how many questions do you think is going to be on the test?
That was interesting. Just, I usually do 3 or 4 multiple choice. The matching is one large problem usually, and that's usually definitions and stuff like that. The fill in the blank will be probably 2 or 3 fill in the blank problems, and then the long answer will probably be 3 or 4 long answer problems. And with the long answer, I will give you plenty of room, and I'm looking for specific things with the long answer. I usually don't take away points for things that are incorrect unless you put that instead of the correct part, right? So, it's okay to word vomit. I'm not gonna be like, oh, you thought that wrong, so you lose points. Okay, and I always do partial credit, so keep that in mind. But no, if I don't see anything on there, I can't grade something that's not there. Okay. If you guys have any questions, please let me know. Gracie, did you send me your test pictures, or did you want to just?
I can do that now. I can
But
go ahead and do that
if nobody else has any questions, you can just stay after.
Okay.
And just like da, da, da. Is Jewel the person that you're working with?
I was working with Rachel, but she left. Rachel Smolin?
Samolin, Smolin, maybe?
Yeah.
Something like that, yeah. Okay. Okay, well.
I guess.
But. Okay. Not a problem. Thank you, guys. And like I said, Grace, if you just want to stay behind. Let me stop recording as soon as I figure out how. Stop recording.